All right. Let's get back on track here. Okay, so here we go. Sorry about all that. We had a lot of papers to collect, a lot of papers to pass out. Now we're finally getting started. Whew. Okay. Should have plenty of time. Plenty of time. So today we're going to start on a new technique for integration. Right? We're going to kind of expand upon our possible, kind of integration. Are things we can integrate. Expand upon that list of things that we can integrate. Right now, we're pretty limited by essentially, if it's got a derivative rule, then we can integrate it. Okay, we don't have too much. Sometimes we can kind of like rewrite the integrand, right? If it's like, quantity x plus 1 squared, we can like expand it out and stuff like that. But there's also many, many integrals that we just cannot do by hand. Okay, we're going to expand upon those. We still won't be able to do all of these by hand. It's, we're going to actually not, there will still, by the time we're done this class, there will be integrals that we still cannot do by hand. It'll be not possible. Okay, but we're going to learn a new technique today called integration by substitution, which involves kind of like a change of variables to help us rewrite an integrand into a form whose integral we can take. So anyway, in this section, we look at how to integrate composite functions. Remember composite functions? That's when you have like a function inside of another function, like f of g of x, right? A function in another function. The major technique involved, like I said, is called U substitution, okay? U substitution just because that's just like the designated variable that we use, okay? You could just as easily use a w or a v, whatever variable you want to use, okay? But typically it's a u, okay? So we just use U substitution, that's what we call it. All right, the objective is to know the few antiderivative rules from before. So remembering those before, like the integral of cosine is sine. The integral of like 1 over x is natural log of the absolute value of x, those kind of things. And then rewrite the integrand to fit those rules. Okay, the role of substitution is comparable to the role of the chain rule in differentiation. It's kind of like a reverse chain rule, okay, a little bit. Simple chain rule stuff, I guess I'll say. Anyway, so here's our theorem for U substitution integration. So we're going to let g and f be a function, or be functions, that are both continuous and differentiable on an interval I. If capital F, right, the normal way we denote an antiderivative of lowercase f on I, then here's our kind of rule here. When we integrate so you can see g of x is inside f, but then outside f, we have the g prime, right? This is exactly kind of, or it's very similar to like the chain rule, right? Where you have a function within a function and its derivative out here. This is like the result of a chain rule, and now we're going to go backwards and say, aha, that is just equal to capital F, the antiderivative of lower f, of g of x plus c, okay? And so another way to kind of think about this looks, kind of messier. We can kind of clean it up, though. If we let u be g of x, so instead of running g of x, we're going to use u, then the derivative of u is going to be g prime of x dx. And the reason how we can do that, maybe I'll do like the intermediate step here. Okay? If I take the derivative of this thing with respect to x, the derivative of u with respect to x is du over dx, right? Equals, and then what's the derivative of g of x with respect to x? Not a trick question. How would we denote that? Yeah, just g prime of x. Okay, times the derivative of x, which is 1. If you want to put a times 1 there, you can. Okay? And so then we get du equals g prime of x dx because we can multiply both sides by that dx in the denominator there. And so we get down to that right there. Okay, we multiply both sides by dx here to get down to that. Bless you. Okay, with this kind of like designation, okay, with this definition that we made here, if u is g of x, then the g of x here will be replaced by a u. Okay, and then since g prime of x dx, that quantity ends up being du, then that can be replaced with a du right there. And so integrating f of g of x times g prime of x dx is going to be equivalent, based on this substitution that we made, of the integral of f of u du, okay, which then equals capital F of u plus c, okay, the antiderivative. So that's kind of the idea. It's kind of a little abstract, of course, without actual functions and like numbers and stuff thrown in there, but that's the idea. Let's jump into like how we're going to actually do this, okay? So in each of these following problems here, the integrand follows that exact pattern that we kind of want to see, where we have f of g of x times its derivative, the derivative of what was inside there. So identify the pattern and use the result to evaluate the integral, then check through differentiation. Okay, so we can see here, for example, letter A. okay, we have a function inside of another function, okay, right? X squared plus 1 is being raised to the 4th power, okay? So our inner function, our g of x, this right here is our g of x, right? That x squared plus 1. It is inside that to the 4th, okay? So the f of x is this outer function here of that to the 4th thing. And then we can confirm that this is g of x because 2x is the derivative of that x squared plus 1, right? The derivative of x squared plus 1 gives us 2x. So there's g prime of x right there. Okay. So we can see it's g inside of f, right? F would be like x to the 4th. F of x is x to the 4th. So, we could say g of x here is x squared plus 1. F of x is x to the 4th. And then that g prime of x is 2x. Right? So you can see all those things. Maybe I'll zoom in on this one so that way we don't have to go too crazy. Okay. Now, prior to today, could we have integrated this thing? Well, not easily, right? I mean, we could have, okay? We could have done x squared plus 1 times x squared plus 1 times x squared plus 1 times x squared plus 1, right? 4 times itself 4 times, okay? Multiply that all out, and then distribute 2x through that whole quantity, and then integrate each one of those individual pieces. But that is a lot of work. So we actually don't need U substitution here, but it's going to be so much more helpful to have it. So here's how we're going to do our U substitution. We're going to change our variables around. And again, if you remember back from our theorem up here, it said to let u be that inside function g of x. So we're going to write let u equal our g of x, which is x squared plus 1 here. Let u equal x squared plus 1. All right, yes, question?
Did the 2x just happen to be g prime?
So if it wasn't g prime, then we wouldn't be able to do this problem. So the problems you'll need to find the g prime in your integrand there.
So they're always going to match up like that then?
Close, or if not the exact same, they'll be off by a constant, like a coefficient, I should say, and that's it. Okay. So and you'll see here. Okay, we'll get to some of those too. So here's u. Of course, we also need to identify g prime here. So we'll take the derivative of both sides. So I'm going to say du dx. Right. We're going to differentiate with respect to x here. So u becomes du dx. The derivative of x squared plus 1 with respect to x will be what? Yeah, 2x, right? No surprises there. 2x. Okay. So one final step here then, du, I'm going to multiply both sides by that dx. So the dx's will cancel there. I'm left with du equals 2x dx. Okay, 2x dx. Which is exactly what we have right here. So let's do some substituting here. Okay, so I'm now going to finally rewrite my integrand. So we're going to integrate, okay, x squared plus 1, what is that the same as? What did we say that was equal to? U. So x squared plus 1 to the 4th becomes u to the 4th. Okay, and then 2x dx, what is that equal to? 2x dx is du. Okay, so we took this kind of more complicated integrand, and through a change of variables and substitution, we were able to rewrite it as equivalently rewrite it as u to the 4th du. Okay, it's important that we both substitute in the u here, and then it's also important that we change that dx to du. Right, we need this dx to become du, because if we have a u in here and we try to integrate u with respect to x, we can't really do that, right? We need the same variables here. We have to match variables. So yeah.
Go back to where you said dx times dy over dx equals 2x times dx.
Like right here?
Yeah. Where did the dx come from?
So what did we do from this step to this step? Took the derivative with respect to what variable? X. So taking the derivative of x squared plus 1 with respect to x, 2x, no problem, right? But the derivative of u with respect to x, this is like that implicit differentiation stuff we do, right? If we had like a y here, wouldn't we write dy dx if we took the derivative?
Oh, yeah.
So since it's a u, we're going to just do du dx. Same idea. Okay?
Yeah, I got it.
Now, rewriting this integrand in this way, we can integrate u to the fourth, no problem. What is the integral of something to the fourth power? It's u to the fifth over 5 plus c. Okay? U to the fifth plus u to the fifth over 5 plus c. This is an indefinite integral, right? So we have to put that plus c in there. And then the last step, we want to, of course, get it back in terms of x. What is u? X squared plus 1. So we just resubstitute in. There's our answer. There's our integral. That's it. Okay, you can say it's 1/5 x squared plus 1 to the 5th if you want to, plus c. Bless you. And of course, we can take the derivative here to kind of show that this is true, right? So if I take the derivative of this, so I'll say like derivative with respect to x of x squared plus 1 to the 5th over 5 plus c. Okay? The derivative of something to the 5th power, we can bring that 5 out front. So it becomes 5 over 5 x squared plus 1 to the, we lower our power by 1, so 4, times the derivative of what's inside by the chain rule, 2x. And what's the derivative of c? 0. It's gone. And so you can see the 5 and the 5 cancel out. There's going to be 1. And there's the x squared plus 1 to the 4th times the 2x right there. So you can see that the derivative here checks our work and shows that, in fact, this is the correct answer. All right? Yes, Gabe.
So I'm just trying to understand what happened, like, to the 2x, like, during the derivative. Like, what exactly, I know it switched over to du, but why did that not get re-implemented into the...
It is kind of there.
You know what I mean?
Like why isn't there a 2x also in here somewhere?
Yeah.
So the 2x and the dx both substituted in place of the du here. All right? Right? There's the d. I mean, you're okay with that part, right? The fact that we did, and then you're okay with the fact that 2x dx equals the du kind of thing?
Yeah.
So when we integrate here, this is telling us to integrate with respect to u, and so the du, and just like the dx, right? It kind of goes away when we integrate here. Just the same idea here. When we integrate that du, it kind of just goes away. Okay, and then so the 2x though will show. You can see how the 2x does show back up when we do take the derivative of this thing. We end up, taking the derivative of x squared plus 1 to the 5, so the 5 goes out front, lowers to the 4, okay, and then times the derivative of what's inside there, the 2x. So you can see it shows back up. Oh, is it off the screen? Sorry, there you go. Okay. So we'll see some more here. Let's get some more practice. So let's look at letter B. Okay. So letter B again, we're looking for kind of like functions within other functions here. All right. In this case, it's maybe not so obvious what we should let our u equal, but we can again kind of like use. Not only do we want to look for let our u be something that's inside something else, we also want to pick our u such that its derivative is also showing up in our integral here. Okay? So, what should we let u equal here? Tangent of x plus 3, exactly right. How can we know we're kind of on the right track there? Well, what's the derivative of tangent? Secant squared. There it is, okay? So you're on the right track for picking the u when you take its derivative and you end up with the other part of your integral here. So let's let u equal tangent of x plus 3. And Bryce, good job on also saying the plus 3 there. We do want to include the plus 3 as well, okay? We do want to include that plus 3 as well. Okay? So we can then take the derivative here. So derivative with respect to x, du dx, is derivative tangent is secant squared x. Okay, and then the derivative of plus 3 goes away, right? It's just constant. And so again, we'll say du then is equal to secant squared x dx. Okay? So there's that. And so now let's rewrite this here. So this integral, that's in terms of x, we'll now put it in terms of u. Okay? Secant squared and the dx, what substitutes in place of that? Du. So I'll put the du here at the end. Okay? And then that parentheses, tangent x plus 3, what's going to replace tangent x plus 3? Just u. So this is the integral of u du. Okay? This ends up being the integral of u du. All right? Or in other words, u to the 1, right? Integral of u to the 1 du. So what's the integral of u to the 1? U squared over 2 plus c. Very good. Don't forget that plus c, right? We've been doing a lot of definite integrals, Now that we're doing some indefinites, don't forget the plus c. All right? We'll get to definite integrals with u substitution tomorrow, okay? Right now we're just focusing on indefinites. In our last step, we resubstitute back in terms of our x. So quantity tangent x plus 3 squared plus c. All right, and there's our integral right there. Instead of over 2, I put it just with the 1/2 out front. Okay, and again, we can check ourselves just to see the derivative. I'll just do that right down here, the check. Derivative with respect to x of 1/2 tangent of x plus 3 quantity squared plus c equals, okay? So the 1/2, we can just leave that as coefficient. Something squared, right, is twice that something times the derivative of the something. The derivative of tangent x plus 3, what's the derivative of tangent of x? Secant squared. And what's the derivative of 3? 0, so it'll be plus 0, so there it is, right? The 2 and the 1/2 cancel, and there's your secant squared times tangent x plus 3, which we have right there. Secant squared times tangent x plus 3. So you can see again, check, it works. All right, let's keep going here. Letter C, 3e to the 3x. Okay. Again, for g of x, you want to pick a function. General guidelines, you want to pick g to be that kind of function. It should be inside, or let your u should be what's kind of inside something else. So what is the function that's inside another function here? 3x. 3x is inside the exponent of e. So we're going to let u equal 3x. Okay? And then we'll take the derivative of both sides. Du dx equals, what's the derivative of 3x?
3.
Just 3, right? And we can multiply then the dx over, so it's 3 dx. Right there. And of course we have the 3 dx right there. There's our du. Okay? So what does this integral rewrite to be? The integral of what? E to the u du. Okay? Prior to today, we couldn't take the integral of this. Prior to today, we were not able to take the integral of this. The only thing we know to take the derivative of, the integral of, we can only take the integral of e to the x. We can't integrate it to 3x, but now we can. Okay, because now we rewrote that as e to the u, and what's the integral of e to the u? E to the u plus c. And so then we rewrite that as e to the 3x with your substitution there for a final answer. Okay? And of course, its derivative, you can just, you guys can kind of mental math that one. That'll match back to 3e to 3x. Okay? All right, letter D. Letter D, we also could not do. Oh, question.
Why? I thought when you multiply by the inside, don't you have to also multiply by what's inside so you find?
Yes. So when we take the derivative, you're talking about taking the derivative of this to check it? Absolutely. So what's the derivative? So let me do this here. Derivative with respect to x of e to the 3x plus c. Okay. What's the derivative of e to the 3x? E to the 3x times the derivative of what's inside, which is a 3. What's the derivative of c? 0 goes away, and there's your 3e to the 3x, right?
Yeah.
So it checks. It works out. Okay. I know, it's weird. It's funky.
Yeah, I flopped it.
Yep.
Right.
Right. I gotcha. Yeah, I know. Right now we're doing two different ways. It's like, okay, we got to keep, derivatives over here, integrals over here, but they do, relate and stuff too. So, yeah. I gotcha. All right. Letter D here. What should we let u equal here? Let u equal 5x. Again, that 5x is a function. I know it's a very basic function, but it is a function inside the cosine. We could not integrate this before today. We don't know how to take the integral of cosine of 5x. We can only take the integral of cosine of x.
Why are there two parentheses?
I think that is a typo. I think it's a typo. Yeah. So let's take the derivative here with respect to x. So du dx equals 5. So du equals 5 dx. Okay. And so you end up here then with, again, there's the 5, there's the dx. So we end up with cosine, the integral, sorry, of the cosine of u du. Okay. Again, folks, we're not like mathemagicking away the x's here, okay? These are substitutions. We are doing equivalent, expressions here and just substituting in. We're starting by defining u equal to 5x, right? Let u equal 5x, okay? There's a substitution, right? We just replaced the 5x with u. That's our own definition. Since we decided that u was 5x, when we take the derivative of x, we take the derivative of both sides with respect to x, we end up with du is 5 dx. There's 5 dx, so that can be exactly replaced by a single du there, okay? This is not just like presto changeo kind of stuff. It's like just equal substitutions, okay? So it's important you do that. Also, one other little thing I want to mention here too. Please make sure you write the word let there, okay? Just saying u equals 5x, from my understanding back when I took calculus, my calculus teacher told us, like, I guess the graders want to see that let kind of indicates that you are designating this to be true, and you're not just saying it's true, okay? Like, I guess you're kind of like making this choice to let u equal 5x as opposed to just pulling out of thin air that u is equal to 5x, okay? So without the let, you're kind of like bringing in this weird u variable that they've never seen before, but putting the let in front lets them know that you are, making this as a conscious decision kind of thing and not bringing it in from some who knows where kind of thing. So anyway, all right. What is the integral of cosine, by the way? Sine. So it'll be sine of u plus c, which is then again sine of 5x plus c. Okay? And so there's our final answer. Please make sure you rewrite in terms of x, right? Your final answer should be in terms of the x there. You should be able to get it in terms of x. All right. For example 1, the integrands fit f of g of x times g prime of x pattern exactly, right? They are all exactly matched up perfectly, all right? You only had to recognize the pattern. You could extend this technique if it doesn't fit perfectly with the constant multiple rule, all right? So we're going to take the training wheels off a little bit, or at least like raise them up some, so you get to balance just a little bit on your own here, all right? But anyway, so example 2, evaluate the following indefinite integrals, so same directions here. But now if we look at this first problem, okay, we want to let u equal what here in this case? X squared minus 1, okay? This one, by the way, do we need to use a u substitution for this one? Do we need to? No, in fact, this one's maybe not that bad if you really, if push came to shove, you could do this one, it's not that awful. It's only something squared. But of course, we're in u substitution, so let's do u substitution. So right, x squared minus 1, that is being squared, so that's kind of like the inner function there. So we'll just say let u equal x squared minus 1. We'll take the derivative of both sides with respect to x. So we get du dx equals 2x, and so then du equals 2x dx. Okay. And now we can see a bit of an issue, right? Do we have 2x dx up here? What do we have? Just x dx. What could I do to this part right here, though, to make it x dx? Multiply both sides by 1/2 or divide by 2. I'm going to multiply both sides by 1/2. So I can say 1/2 du is equal to x dx. Right? Equivalently. Right? I'm just multiplying both sides by 1/2 there. So, when we go up to do our substitution here, when I replace x dx, what am I going to replace x dx with? 1/2 du, right? X dx, we have this little equation right here. X dx is 1/2 du. So when I replace x dx, I'm going to replace it not just with a du, I'm going to replace it with a 1/2 du in this case. Okay, just 1/2 du. So let's rewrite that. So I'm going to put the 1/2 out front. parentheses, x squared minus 1, what do we replace that with? U, right? So it's just going to be u squared, and then du. Okay, so there's our x dx right there. Okay. I like to put the 1/2 out front just because we normally have the coefficients in front. If you put if you put u squared times 1/2 du in the back here, that's fine. Okay, but I like to put the coefficients out front. Right? It's all one big product anyway, so it's fine to put that 1/2 out front like that. Okay. Okay. Can we integrate this? Yes, it's just a coefficient, right? So we can leave that coefficient 1/2 in front. What's the integral of u to the 2? U to the 3 over 3, right? And then plus c. Okay, so this becomes 1/6 u to the 3rd plus c, which is then 1/6 times x squared minus 1 to the 3rd plus c. Questions on any of that? There's that. All right, let's continue on here. Letter B. All right, letter B. Integral of 7 times the secant of 4 theta times the tangent of 4 theta d theta. What should our u be here? Tangent 4 theta? All right, so let's try that. U equals the tangent of 4 theta. What is du going to be? Secant squared of 4 theta times 4. Do we have a secant squared in here? No. Okay, so we don't want our u to be tangent of 4 theta. But this is okay, Mario, because this is what you're going to be going through as students, right? Mr. Wade's not going to be, standing over your shoulder saying, let u equal this, right? You're going to have to figure it out. And so sometimes you're going to choose wrong. And it's important for you to be able to diagnose, I did not choose u correctly here. Let's try the other option here of secant of 4 theta. Okay. Right, so obviously tangent's not right. Is secant of 4 theta right? Well, if we go to take the derivative of this to get our du here, what's the derivative of secant? Secant tangent. Well, we do have secant tangent, but this secant is going to be taken up by our u, and so we're not going to have a secant and a tangent left over, right? This secant is going to be replaced by u. We'll only have tangent of 4 theta d theta. We're going to need a secant of 4 theta, tangent of 4 theta. So this is also not the right u. So what is our u? Landon? 4 theta. It's only 4 theta here. Okay, only 4 theta. Because we'll take the derivative here with respect to with respect to theta here in this case. So the derivative of 4 theta is 4 with respect to theta there, and so we get du equals 4 d theta. Okay. Now you'll see here we have a 7 d theta. Okay. But this 7, we can kind of pull that 7 out front of our integral if we want to, and make it 7 integral secant 4 theta tangent 4 theta d theta. So by the properties of integrals, right, we can pull that coefficient in front of our integral symbol. And so now, okay, all we have in our integral is d theta. Right here, do we have just a d theta? What can we do here to get d theta by itself? Yeah, divide by 4. So we can say 1/4 du is equal to d theta. Can we move that 7 kind of out front, all right, because it's just a coefficient, so we can pull that out front of the integral. And so all we need is a d theta here. And so now we can finally rewrite this whole thing as 7 times the integral 1/4 secant of u tangent of u du. Right? That d theta became the 1/4 du. Secant of 4 theta, secant u. Tangent of 4 theta, tangent u. Okay? What can we do with this 1/4? Bring it out front with the 7, make it 7/4. Okay, and then we'll do secant u, tangent u, du. And what's the integral of secant u, tangent u? Secant of u. So 7/4 secant of u, good, yeah, plus c. And we'll make our resubstitution here. It's going to be secant of the 4 theta plus c. Okay, and so there's our final answer back in terms of theta. Okay, question, Gabe?
What was 7 put onto the O?
Just because when we had this right here, we had 7 d theta, and we wanted like 4 d theta, in a sense. I mean, you can leave the 7 in here. You can leave the 7 in here if you want, and then just do what we still did right here. With, so this makes sense about what we had. We just substitute the d theta for 1/4 du in for the d theta, so it'll be the 1/4 times the 7 ends up still getting the 7/4 there. So you can leave the 7 in the integrand if you want to, and then just substitute in for the d theta with the 1/4 du and stuff. Okay. So, all right. Other questions? We're still good? Keep going? Okay. Let's try letter C. All right, letter C. What should we let u equal here? What is the function inside of another function here? One minus 2x squared. Let's try it. What's the derivative of 1 minus 2x squared? Well, derivative of 1 is 0. Derivative of minus 2x squared is minus 4x squared. Whoops, minus 4x. Goodness gracious. Yes, minus 4x. Okay, the 2 comes down, right? Negative 4x. Okay. Getting ahead of myself here. Okay. We'll multiply the dx over, so we have du equals negative 4x dx. Of course, we have negative 5x dx. Okay? But again, we can kind of we can think of it a couple different ways here if you want to, all right? We can pull that negative 5 out. So we'll say negative 5 times the integral of x over 1 minus 2x squared dx. Okay? So there's our x dx. We don't quite have x dx here. What do we need to do to both sides? Divide both sides by negative 4 and multiply both sides by negative 1/4. So we get negative 1/4 du equals x dx. And now we have exactly what we need for up here, for there's the x dx right there. Okay? So we'll rewrite this. The negative 5 will still be out front. Integral. Okay. X dx gets replaced by negative 1/4 du. So I'm going to put the negative 1/4 out front here. I'll make it 1 over u squared du, or du over u squared if you want to write it that way. Okay. So there's our substitution. The x dx becomes negative 1/4 du. Okay. And so we get 5/4 integral 1 over u squared du. Right, negative 5 times negative 1/4. And then how should we maybe rewrite this before we integrate it? Instead of 1 over u squared, what should we write? Yeah, u to the negative 2 du. Okay. Is this integral going to be natural log? No. Why not? It's negative exponent. It's not negative 1, right? Only when we do u to the negative 1 do you get natural log, right? This is just going to be 5/4. We add 1 to our exponent here, so it's u to the negative 1, okay, plus, or over negative 1, I should say, plus c. And so we end up with that negative 5/4 again. That's okay. Okay, and then we'll plug in the 1 minus 2x squared to the negative 1 plus c. Okay, and resubstitute back in there, the u. Okay, so the over negative 1 I put with the negative 5/4, and then u to the negative 1, put the u in. And I guess we could finally put, 4 1 minus 2x squared like that. Okay, if we really wanted to put it all back together there. But of course, this is fine too. Or this even. Okay, all those are good. Okay, questions on any of that? Yes. Yeah. Okay, Question, Shelby.
You not have to. Oh, wait, never mind.
Okay. So that's the idea there. Yes, Lily.
How would the first one you start off incorrect and you say you have substitute?
Oh, you know what? You're right. Thank you. Good point. Not back in terms of x. Not back in terms of x. There you go. Good point. All right. Good now, Gabe? Or you need me to still stay on that? Okay. Well, okay. No problem. No problem. Okay. All good. Good. Okay. Let's look here at letter D. All right. Again, maybe not so obvious here what our U should be, right? These both are kind of like, I mean, you could say, okay, well, that's like kind of like a U, but that could be like a U too, right? It's like a product of things. But remember, you also kind of want to pick your derivative you want to pick your U such that the derivative of U is also present in your problem here. So with that as kind of our guideline here, do we want to pick the first thing to be our U, or do we want the second thing to be our U? Again, you want to pick your U such that the derivative of that U is also showing up here. So we want to pick this to be our U here. Okay, now we have a couple options. Okay, option one, we could factor a 3 out of this. Right? Couldn't we just take a 3 out of this right here if we wanted to? They both have, it's 3 to the x plus 3x. So we could factor 3x out. Let's just leave it the way it is. We'll just let U, for right now, we'll let U equal 3e to the x plus 3x. We'll just do it this way for right now. Okay. Again, we chose this one because its derivative is going to show up right here. So we'll do du equals, okay, du dx equals 3e to the x plus 3. We'll multiply both sides by dx. So we have du equals 3e to the x plus 3 dx, right? That quantity times the dx there. Okay. Do we have 3e to the x plus 3 dx? We have e to the x plus 1. What can we do to this to make it e to the x plus 1 dx? Yeah, we can factor 3 out. Okay, if we want to first here, just to kind of show the. Okay, the 3 factors out right there. There's our e to the x dx, e to the x plus 1, sorry, dx. We'll divide the 3 over, so 1/3 du equals e to the x plus 1 dx. And there is exactly what we've got right there. Okay, so it's the integral of u times, or 1/3 u du, I guess we'll say. 1/3 u du. So there's our 1/3 du right there. We just substitute in place of the e to the x plus 1 dx. And then their u is 3e to the x plus 3x right there. Okay. So we have 1/3 times integral of u is u squared over 2 plus c. So we have 1/6 times 3e to the x plus 3x squared plus c. Okay, re-substituting in back to those u's. Okay. Questions on any of that? Yes.
Where did the u squared over 2 come from?
The u squared over 2. That came from the integral of u. Right, we were integrating the u.
Oh, yeah.
U to the 1,
Oh, yeah.
which then becomes u to the 2, divided by the new power 2.
And then the 1/3 is just du, right?
The 1/3 is from our substitution of the du, yes.
Okay.
Okay, thank you very much. Okay? Good on that one? All right, let's go to the next one. So we're going to do these 4, and then that's it. Okay, we're just doing the rest of these 4 here, okay? All right. What should our u be here? Again, what is inside of another function? So let's kind of take some thoughts here, right? So we could let u. That looks like let u equal. So we could let u equal like the 5th root This is not x to the fifth times the square root. This is x times the fifth root of 6 plus natural log x. So it's the fifth root, and that's just x. We could let u be the fifth root of 6 plus the natural log of x. But when you do the fifth root, its derivative, you're going to have another fifth root there, and there's no other kind of like fifth roots showing up. So we don't want to let u equal the fifth root of this thing. That's too much. We don't have its derivative there. We could let u equal x, and we would have the derivative of x here. It's just 1, so that would like show up. But then we would still have this fifth root of 6 plus natural log of x that we just didn't deal with, that we would ignore. Okay? When we use a u substitution, everything must be rewritten in terms of u. Okay? Everything must be accounted for except for these coefficients that you can pull out front. Right? But all the x's need to be accounted for and be rewritten in terms of u. So let's let u equal what's inside the fifth root there. 6 plus the natural log of x. Okay, 6 plus the natural log of x. What is the derivative with respect to x of 6 plus the natural log of x? Just 1 over x, isn't it? Derivative of 6, 0. Derivative of natural log of x is 1 over x. So we get du equals, du equals 1 over x dx. Do we have 1 over x dx in this problem? We have 4 over x, which we can then pull that 4 out front and make it 1 over x, right, times 1 over. Let me just rewrite it like maybe more explicitly here. Is this not the same thing as the original problem there, right? Wouldn't it all multiply back together to be the same thing? It would. It would, okay? And so this 1 over x dx, what do we substitute in to replace 1 over x dx there? Just a du. And so we have 4 integral 1 over the fifth root of u, and then the du on the outside there. Okay. That's it. And so then we're going to rewrite one more step here. 1 over fifth root of u is u to the negative 1/5, right? Because it's fifth root. So 1/5. And then don't forget the du. Wow, so this mess of a problem rewrites to this. Not bad at all, right? And so we integrate that. We add 1 to our exponent, so we get u to the 4/5 over 4/5 plus c. Dividing by 4/5 is the same thing as multiplying by 5/4. So we have 5/4 times 4 times, and I'm going to go ahead and substitute in for the u, 6 plus natural log of x. Oh, I should say, yeah, natural log of x to the 4/5 plus c. Okay, if you want to, you can say, okay, that's 5 times 6 plus the natural log of x to the 4/5. Not necessary to have the absolute value with our natural log here because we didn't integrate. We did not integrate to arrive at the natural log here. The natural log is just part of our u substitution, right? Just part of our substitution. So we did not integrate to arrive at the natural log. We didn't integrate 1 over u to get natural log of the absolute value of u. That was just part of our substitution, so we don't need the absolute values there. All right, all good on that one? All right, let's go to letter F then. All right, letter F. So, what should our u be here? What is a function that's inside of another function here? Cosine squared in parentheses. Should we let u be cosine squared? No. Because we take the derivative of cosine squared, we're going to have 2 cosine sine. And we'll have the sine, but we won't have another cosine because we already used up the u for the cosine squared. So u should be what? What's inside something here? So x, if we just do x, it's just gonna make it 3 cosine squared u sine u du, and that's gonna get us back in the same place we were before. So we can't let u just equal x here, unfortunately. It won't be quite enough. So we want to let u equal cosine here. Cosine of x is being squared, right? We can think of this as integral 3 cosine of x quantity squared sine of x dx like that, right? Isn't it the same thing? And so that cosine of x is inside, it's being squared. Is cosine's derivative in the integral? Is our u, our cosine of x here, is its derivative in the integral here? Yeah, it is, right? There it is, okay? So, derivative with respect to x, derivative cosine is, oh, right, yeah, this is where you got to watch those SIGN signs, right? Okay, negative sine of x is the derivative, so du equals negative sine of x dx. We don't have a negative sine of x, we have a positive sine of x dx, so we'll move the negative over here, right? Divide it over, multiply it over, what do you want to say? So negative du is sine of x dx, there's sine of x dx, there's sine of x dx. And so we'll end up with the integral of negative 3 u squared du. So we've transformed trigonometry into integrating just a polynomial, okay, or really a monomial here. Remember, this substitution is not integration yet. All we're doing is rewriting the integral into a form so we can finally integrate it, right? All this work, it's not integration. Now we're going to finally integrate it. Negative 3u to the third over 3 plus c. So the 3's will cancel. We're left with negative quantity cosine of x cubed plus c. Okay. Questions on any of that? Okay. Let's keep going here then. All right. Letter G. The integral of sine squared of x over 3 times the cosine of x over 3 dx. Okay. So again, remember that this is equivalent to saying the integral of the quantity sine of x over 3 squared cosine of x over 3 dx, right? So what would be a good candidate for our u here?
X over 3.
What's that?
X over 3.
So just x over 3, if we let u equal x over 3, then its derivative, okay, will be 1/3, right? The derivative of x over 3 will be 1/3. We can, and we can make the du equals 1 over 3 dx. So we'll have sine of u squared times cosine of u, but can we integrate sine of u squared times cosine of u? Do we know what that integral would be? So yeah, no, that won't work. Okay, so we don't want to let u equal x over 3. Okay, so you went too far inside, right? I see what you were thinking there, maybe, Clayton, is that you're thinking, okay, it's inside the sign. X over 3 is inside the sign. And that's right, it is. But we need to go just a little bit bigger. Sine of x over 3 is what we want. It is inside the square. It is inside the square, right? It is being squared. And so what is the derivative of sine of x over 3? Well, derivative of sine, cosine of x over 3, times, we have to use the chain rule here, times derivative of what's inside, times 1/3. Okay? Looking back at our integrand here, do we have cosine of x over 3 times 1/3? Close. We have cosine of x over 3. So let's multiply the 3 over here. We'll have 3 du equals cosine of x over 3 dx. Right? There's what we were looking for. And so this will rewrite as the integral of 3 times sine of x over 3 squared becomes what? U squared, okay, times du. Okay, I put the 3 du right there. Okay. So again, wow, this crazy mess with trigonometry and stuff like that, it's really ending up, we're just going to integrate a monomial here. So 3u cubed over 3 plus c, which is then cosine of x over 3 cubed plus c. Did I mess up? Oh, it's sine. Doggone it, you're right. Do as I say, not as I do, right? Actually, no, don't do as I say because I definitely messed up. So don't do as I say or as I do. Just listen to other people. Okay, sine of x over 3 cubed plus c. Last one. Last one. I know we're really pushing here to the edge, guys. That's because we went over the quiz and stuff like that. So, all right. Last one here. All right. What should our u be in this case? Tangent of x. Okay. So let u equal the tangent of x. Okay. So what is the derivative of tangent? So yeah, derivative with respect to x here of tangent of x is secant squared x. Okay, so we get du equals secant squared x dx. That is exactly what we've got right there. And so we can say this is just the integral of what? U du. Okay? Integral of u is u squared over 2 plus c. So we have 1/2 times tangent of x squared plus c. Did anyone think of an alternative u here? Yeah, Sarah?
U equals secant of x?
Aha, so we could, in this case, let u equal secant of x, okay? Because isn't secant squared tangent x, that's the same thing? Well, we'll get to that anyway here. So let u equal secant of x, du then is, what's the derivative of secant? Secant x tangent x. And in fact, we would have that as well. Right? When you take your u here of just secant of x, we can rewrite this as secant x times secant x tangent x dx. And so this ends up also being the integral of u du here. So we get 1/2 secant squared of x plus c. That's what you got, right, Sarah? Yeah.
That's still right.
So yes. So interestingly enough here, okay, but it should be right. I'm pretty sure, yeah. Yeah, I think so. I'll take a look at that though, but I think it should be. Okay. All right, well done, folks. We made it.